Good morning, everybody. Thank you for joining today. Today we're going to review the OMA's processor. The OMA processor is actually MIPS architect. My name is Oskar Nava. Today's Wednesday.
What's OMA for?
Coming on. In our agenda, we're going to see the company, we're going to see the OMA processor, enhancements, future plans, questions. Do you have any on the end? The company, the name. The name of the company, or why I decided to call it OMA, is actually because of people who always support me, which are my two brothers. And I use the first letter and the second names to create a unique name. That's the reason why the name is so important to me. That's why the name of the company and the name of the first processor of this company.
Good.
OMA processor. OMA processor is actually we use the MIPS architecture. The reason we use the MIPS architecture because the MIPS is actually a reduced instruction set computation, which is mean RISC. That means it's very basic. When I say basic, I mean in the more low-level implementation is basic. Everything is 32 bits wide. Everything, all the data points are the same size. Instructions are the same size. This actually helps. Just a little fun fact. Matter of fact, MIPS actually started as a school project. It didn't start as an overall outside project for like Intel. The professors and students were talking about how hard was actually learning Intel because everything is different in Intel. All instructions are different size.
Right.
The way you add everything is so different. So they create actually MIPS used for teaching purpose. And
Right.
But after a few years, they actually came to the market and they're very good processors. Very useful in the company. We have different data types. The data types that we use, for in OMA processor is actually sign-on, signs. That means we can add, subtract, any kind of data we have unsigned. We use registers. We have registers that this is again because it's a RISC processor. Each register is a 32 bit wide. All of us are the same. None of them is low. Doesn't matter if you do a J type or R type or I type instruction. They're all going to be 32 the size, and well, we have 32 of those. Just 32 because that's a pretty good number, and it's going to keep the cost of the processor very, very adequate. Addressing modes. The first addressing mode we have is immediate. The immediate addressing mode immediately is the operand. The operand is an email value stored implicitly in the store. Like ELI is we have the register 11. We load it immediately with the register 3. It's very simple. We have this number goes straight to this register. It's very immediately. So that's the reason we use that one. We also have the registers. Why we use the registers? The registers are actually in the most part, we use the register as to calculate it. We do everything with the register. We add, subtract that in order to calculate the value in the register, and we use it to link into their. Oh, sorry. It's on the indirect mode. Actually, we use the value of each register as a pointer to the memory. It could be go to the memory of the data memory, or it could go to the I/O memory, straight to it. Or we can actually go and get the value into the memory. But we calculate the address using the value of the registers as a pointer and as a direct. Instruction set. Again, all instruction sets are 32 bit wide. We divide into 6, 5, 5, 5, 5, and 6 bits. If we add down, numbers are actually going to be from 0 to 31 bits. And most of them we divide this way. One of the ones, the first one we're going to see today is actually the R types. R type use the first 6 bits, or the most significant 6 bits, to use the output. Every time that these guys are 0, we use these 6 bits to tell us either R type, J type, or I type. The way we do this is because this way it allows us to have more variety and more more functions. In this case, in R type, we use this guy. When it's all zeros, we actually goes to the functions, which is also 6 bits. And we read these 6 bits, and with these 6 bits, we decide what to do. We can do it adding, subtracting, multiply, divide, any kind of hard type instruction. With the I type, we actually, the same thing, we also have all this from 0 to 31, but in this case, we only, the output stays the same, 6 bits, this is 5 bits, and we have the addressing immediately. We use normally this one to do the branches, transfer the branches. I type. In the I type, we actually use for jump. In this case, we only tell the what kind of jump we have with the first 6 most significant bits, and then the rest of the bits are actually used for the tagging. But here, from 0 to 24 is just immediate the target of the address, and from 24 to 31 we use it for the output to tell what kind of jump we want. So as you can see, we have we have a lot of choices that we can do. We can do a jump link, jump R. Okay, so the architecture of the OMA architecture. In a very simple way, we can say we have the CPU that has DY2 that's coming from I/O memory. We have DIY that comes straight from data memory. We have the CPU send the address to both, and we tell them what address we want to look at it and what data. If we're doing store, what data we want to store, or if we're doing a load, we use to send this one to send back the data that we want. Well, we use DY to get data, but we use this guy. We have a control, a gentleman that does the controlling part of it, but we're not showing here just to show you a overall picture. If we go a little more into detail, actually, you can see that inside the CPU, we have actually the instruction unit. The instruction unit is the guy who has all the instructions into it. We can load and unload this guy with different instructions, and every time we load instruction, it will do something different. We have the internet pad. This is actually the pad that we use in order to tell the data what to do. We play with the data, and of course we have our data modes. Here's the instruction unit. The instruction unit, the first thing we did is we decided to put a little register here, multiplier, to decide if we want the PC. That's mean the data that we calculate, we send it back, we use the PC. Or we can have these 2 elements. The one we're going to use it for branches, and the other one we're going to use for jumps. And of course we have select, and that's it. Then after that it goes to the PC, where we start from 0 all the way to any number of instructions we want. It tells the instruction unit what instruction we want, and we select these ones, which these guys we control if we're reading, writing, or subtracting. And we also have, this is actually very important guy, because this guy saves the instruction.
Yeah.
At this point, we can use send instruction right away, and in the multiple, in a single cycle, it will work perfectly. But since we're thinking about multiple cycles in the future, even pipeline in the future, we're gonna need something to hold the data for different cycles. So that's why we decided to go in and get this guy, so we can have the data there for one entire subclass, so we can have it. And we have the same section there. So we use the first 16 bits, and then we transfer it to 32 bits. Here we have the integrated data path. Like I say, I/O comes, and we get the S address, the D address, and the T address. We get this guy. We get 32 bits register inside this guy right here. Why we have it there? Because it's faster to get the information that we need and everything. And again, we can send this guy the data from MS and T straight to the ALU and make it what we need, and then straight from the ALU can go back to A out, and we can have the AD out, so we can have the right information. However, we decide to implement right here these registers and these registers. The reason that these registers is because we're thinking about multiple cyclings and pipelining. So in order to have pipelining or have multiple cycles, we need to have our registers, or they actually save for at least one cycle, so we can have it ready for the future. So instead of going back to the drawing when we decide to implement pipelining, we already thinking ahead, and we already putting some registers around the important parts. We have these mods. It goes from TD, that is actually sign extension, and we have for D, so we can decide if we want the sign extension, or we have actually the data in T to do the jump or branches or anything we need. Or we also have this guy right here that controls the the S address. We can get S address or the point or the stack pointer address right here, so we can decide what we need to, which one we need, we can pick up. And here we also have this for branches and jumps. And the mux right here controls the TS, and we have control the flags and the out. This guy controls both the out from memory and from the I/O, and we have the select.
What's the mux right on top of that?
Which one? This one?
Right on top of the mux that has DY or from memory or IO. It looks like it's pointed the other way.
Oh, it's not a mux, it's a register flag.
Oh, that's a register.
FRE, register flag. It holds the registers and the
Flags register, okay. Got it.
And wasn't able to make it rounded, so I decided to go with this and then we have actually what we got, the LEU. The LEU does all the calculation for us. At this point, we haven't made it with MIPS32, which does all the adding, subtracting of it. We have divided and multiplication. This deals with the multiplication and dividing, of course. And we also have the shift vary. This guy does all the shifting. S goes to all ones, and T goes to choose 3 of these 2 because this one doesn't have it too. And FF, we use actually FF for tell them to because they all work at the same time. When we send data, they all start working. So with this guy, the FF, we told this guy what we want to do, if we want to do add, subtract, so forever. And it tells this guy what kind of shift we want. But they all produce data. So we also use this guy for this mux A to 2 to get all that we want. To tell them, okay, we want these guys output, or this guy, or this guy, or this guy.
Right.
So that way, this way is very easy because we want to be, in the future, we're actually thinking about adding more at least here. So this guy is going to expand.
Right.
And the easy way to choose it is using this guy.
Good.
So that way we don't have to deal with anything inside
Right.
these elements right here. Enhancements. In this project we have rotate right, which actually it have a new RTL. To keep it simple, it's also a 32, 0 to 31 bits long. But in this case, we usually use a function same as R, it will be like a type of R type because we use 0, 0. And we thought to go to look at this function here to decide what kind of shipping it is because we have to ship in this moment. We have rotate right, rotate left. And we use this gentleman right here, shaw. So we tell how many rotations we want in each side. We're not using RS because we don't need it, because we're just shipping RT. But we need RD because RD will get actually the data that's coming. So that's what we're going to save all the data. So actually here is what we just explained. Here is the new operation. The T, the D, H represents how many numbers of bytes we want to move to this guys, and the coding is this way. The first bit is zeros, the other one is 1A, and the
So
T and
the HHH is the shift amount, huh?
1A.
The H's are the shift amount?
Yeah, the H is the shift amount.
Okay.
And the H is the shift amount.
Okay.
And this guy is the encoding, so tell her that we're gonna go and do this guy.
Was that a spare
This one,
opcode?
That's a spare one, so
Okay.
we have a bunch of ones, so we decide to use this one.
Okay, good.
Here's actually the code. This code is actually running. This is how we decide When we go, we rotate right, we give it we tell. In here we have two cases. The first case is actually this one. This is FF. This is actually comes from FF. They'll tell later on. This tells us to rotate right. And inside that one, we have another case that decides how many rotations we're going to have. That comes from SHMT, which is the age of the previous slab. So we tell this many times we want to rotate. So let's say we want to rotate one time. We get the first bit, we put it to the right side, and then we shift everything to the right.
Mhm.
Pretty simple.
Very good, though.
Seems explain. For the L rotate left, we use the same kind of architect, the RTL, function, not in use, that is not in use, RT, RD, and CHOP. Same. The only thing difference, we don't use it, we use 1B, not 1A. This comes from the FF. So also again, same concept. With the FF we decide to come with this guy, and with the shop we decide how many times to rotate, but instead of rotating to the right, now we rotate to the same concept. Future plans is to create actually power up. Power up would be like 2 to the 3, 2 to the 4, 5 to the 5, any number you want. It will be unsigned, so we can do more numbers. And it will be a 64 output. We'll explain how we're going to deal with that because, like I said, everything's supposed to be 32 wide. So how we're going to have actually a 64. We go over that a little detail right now. And this is actually a new code, one FF, and I use the output. And this time we're actually using IS, RT, and RP. We're using actual OT. But we're not using any of this.
Where are you going to store that number?
Right coming out. Don't worry.
Okay.
The power up we actually have already. We're already working on it. My team is already working in this. What we're gonna do, we're gonna have S, T, and P. Which, well, the first thing we do, we tell us 32, same. But we have P, which is 64. This guy. And in order to make it work, we have to actually make an inter A and B, and we transform this guy to. This is very important because if we don't do this, it will not synthesize. And if there is no synthesize, well, we need something that doesn't work. We need to make it work.
Right.
So that's why we did this part. And then it's simple. A to the power of B. Very simple stuff.
So double asterisk is a power-up operator?
Power up, yeah.
Verilog does that?
Yeah, but it only works in integers. Doesn't work in
Unsigned?
in science.
Yeah, right.
Here's a little, very small storage. Apologize if you cannot see this. We have the base, which is 5. We have the T. We have 2, 5, A, and 0, D. If we have 5 to the 2 power, we have 25. To the 5 power, we have 0, C, 3, 5, and if we go to A, we're going to have this big number. And if we got to a bigger number, we have this one. This is what it's important to have 64 bits and not 32. Because if we have a 32, we're not going to be able to handle this big number, which is huge. I don't recall the number right this. I don't have it in my head, sorry. First thing we have to do, another module.
Mhm.
Why we do this? Simple. So we don't have to touch any of this. Because all this works, so we don't touch it.
Right.
Don't touch what works. Don't
Right.
fix what is not broken.
That's right.
So FS comes straight to tell us what to do. We get S, we get T. And the great thing about it, since this guy is already in here, we only have to make a space for this guy right here, which we have. And say we decide to go low or high. And of course, what flags coming up. In this case, we're going to have no flags because it's on sign. Here is what we're getting. Here is the big thing, the big goal. We need to have high and low. The same way we work with the multiplications. I didn't explain sorry about that. Multiplication columns, and they store it here so when we use it once to use it, we can use it. We're gonna do the same thing but with a P high and P low. These guys are gonna be controlled with their own low end control. So when the user tells us to do that information, it's gonna stay here. and it will stay there as long as the user wants. If he wants to have it there, the only way to get rid of these guys would be with a reset or with a new input that we decide to put it. This way will allow us to do all the calculations and then come back and refer it to the top part or lower part of the information. So we can do all the calculations.
Let's talk about that just for a sec while we're here. So you hold it there in P high, P low instead of high low, because you could have put it in high low.
Yes, but what about if a user wants, for some reason, wants to do a subtraction?
Inevitably, whoever did the exponential or the multiply or the divide, they're going to want to put that data back in the register file typically.
Yeah. No.
So we have a move low and a move high instruction. So are you going to add another
Yeah, we're going to add
move P high, move P low?
That's the next, well, we don't have it here because we're actually working on that.
Yeah.
But yeah, we're going to have to add P high, P low in order to have it into the ratio.
So I want you to think about that, because if it went just to high-low, somebody would do the exponential, the power instruction, and then they would do move high, move low, and put it in the register file. And then they'd do a multiply later if they wanted to do a multiply or divide. But, you know, I don't know if it's worth the cost of adding 2 new registers and having 2 new instructions. Because the concept's the same. You're getting a 64-bit result
Right.
for exponential. Store it in high and low and let them move high, move low when they want to. Because usually you don't do multiply and then a power and then a divide. Let's say I wanted to do multiply, divide, Oscar. Multiply and divide. I've got to move it anyway.
Right.
So it's more efficient, I think, and more cost efficient if you just have it in high-low. But the concept's the same, you know, it's just you don't want to pay for stuff if you don't really need to pay for it.
We have to think about this a little more and probably take that into consideration.
Because you'd have to add those 2 new instructions just for that, where you already have instructions to do that type of
we can
thing.
just switch the name of the instructions to low, high, and that way it'd be.
No, it'd just be move P high, move P low. You know, it's something to think about it. When you do design, it's like, if you don't need it, if you can get by with what's there, currently there, with the same instructions, go ahead and use it.
Mm.
But a great idea.
Yeah.
Okay, keep rolling. You're doing good.
Then after that it will be pipeline. Like I've been telling to this point, and actually that's another reason why I put these guys right here.
Yeah.
And think about you reusing this. But the main reason of having this right here, in the IR that we see right now, is because we're thinking about going pipeline in the
Exactly.
next level.
Exactly.
We're gonna need to have these elements right here that we have already. We only need to make this here that.
Right.
But we already have this. We can save all this information. We already doing it. So we're already in the step advance of pipelining. So we're thinking about it what's coming next. However, that doesn't stop there. With our control unit, we see the units, the control signals has to be saved as well.
Yeah.
So we're gonna need to make actually 1, 2, 3, 4, 5, 6 new registers that will hold, for each step will hold one part of the instruction.
Right.
Doing this, the pipeline will work. In some cases. What are those cases? Well, sometimes, let me go back. Sometimes we're gonna need, well, this is gonna work for the instruction. But what about if this guy is telling me that we need to do this guy and we cannot do this because this is in here, but we need it here. So what we need to do is something that's called forward instruction, so we can get the data, the right data at the right time. So we're not by doing this, that's not pipelining yet. So we need to introduce this guy that does this. But even with the forwarding machine, we're gonna still have some sort of problems. So we're gonna also have to call a new guy. That new guy would be height segment detector and the forward unit that will be here. This will actually deal with all these problems that we coming up. At this point, we're not sure how many problems and how many deals we have to do. It's still in process. But we know we're going to have these elements in order to keep going with the pipelining. So we already know where some of the data is coming, but we still need to figure out a little more.
Where'd this diagram come from?
This diagram just comes from a website.
Huh?
One of the websites that I used to refer.
Okay.
Just to show the idea. And that's it. Any questions, comments?
Excellent job. That was a great job. Very good.